Okay, just a final remark to the epsilon entropy typical sequences. So in information theory, you already had that we can replace sometimes the entropy with the differential entropy. There we prove the capacity, for example, for the first for the decreased memory channel, and then we go from the discrete case to the continuous case. And there, in many cases, we saw that we just can replace the entropy with the differential entropy. And if you just make a check what we did until now and look at the slides or in the script, then you will recognize that we can replace all probabilities with density values and the entropy with differential entropy. And all probabilities still stay the same. Now we will come to some other definition of typicality. So in this case, we say a sequence xn is epsilon letter typical with respect to epsilon on px if n(a)xn, so the number of a's in xn, over n minus px of a is less or equal epsilon times px of a for LA. In some books, it's only written less or equal than epsilon instead of epsilon times px of a. But the main property is still the same and all theorems stay the same. But the proof of the theorem is a little bit simpler perhaps with this notation, and some of the basic properties are a little bit more useful perhaps, or makes more sense. Perhaps it's easier to see what happened if you look at formula 11, which is just a reformulation of formula 10. So there we have 1 minus epsilon times px of a is less or equal the numbers of a in xn over n, less or equal 1 plus epsilon times px of a. So the set of xn satisfying 10 and 11 is called the epsilon letter typical set with respect to epsilon on px. And it is denoted again with Tn epsilon of p of x, this time without a tilde. So in this time we don't speak about the expected value, we just directly somehow count the number of symbols in the sequence and estimate it by its probability. Let's look at some examples. So the first example is a binary source. For a binary source, we have just two probabilities. So let's assume the probability of 0 is 1 minus p, and the probability of 1 is p. Then we can simply write the formula 10 as 12, where you have n, the number of ones in xn, over n minus p is less or equal epsilon times the minimum of 1 minus p and p. Why is it possible? It's just possible just if a is equal 1. I think it's clear, you just insert in 10 p and you get the formula. You have perhaps to think a little bit about the minimum. And the second case, if a in 10 is 0, then we just replace n0 of xn, so the number of zeros in xn, just by n minus the number of ones in xn, because it's obviously just two symbols and they are the same. And so you have there n minus n1 of xn over n minus, and now you have there 1 minus p. And if you evaluate it, you get again n of 1 xn, so the number of 1 in xn, over n minus p, less or equal epsilon times the minimum of 1 minus p in p. The second example is if px is uniform. Then one could expect that all sequences are perhaps letter typical, perhaps all because all sequences have the same value, perhaps also the sequence with all zeros is letter typical. Is it really true? Just let's think a little bit. So if we have a uniform distribution, then the probability is just 1 over x for each symbol. So let's take any symbol A. So now we look at 11. So and put in for px of A 1 over x. And then we put out to both sides. Then we get there 1 minus epsilon times n over x, lesser equal than the numbers of A in xn, lesser equal than 1 plus epsilon times n over x for all A in x. Now let's think about when is this every time fulfilled. So if you get something which is smaller equal 0, of course n, the number of a's of xn, is always between 0 and n. So that means if the right-hand side is smaller than n, then not all sequences are letter typical. Let's think a little bit if this could be. Just look what is if we put in x minus 1 for epsilon. If you put in x minus 1 for epsilon, then we have exactly n there, because then we have 1 plus x minus 1, that's x, and then we have x times n over x, so we get exactly x there. That means if we choose epsilon smaller than x minus 1, then not all xn are letter typical. That's also an important feature. Now let's think what is if px of A is 0. Then look at 10. If we put in there px of A equals 0, then we have there just the numbers of A in xn over n is lesser equal than 0. That means that that na of xn must be also 0, because otherwise xn is not typical, because it couldn't be lesser equal 0. The next case is the other way around. Let's think what then happens. Let's assume that px of A is greater than 0, but the symbol does not appear in the typical sequence. Then na of xn is 0. Then let's put it into 10. That means we remain with px of A lesser equal epsilon times px of A. But epsilon is small. It's of course smaller than 1. That means every element which have positive probability should also appear in a typical sequences. So the next thing is in principle very similar to the first theorem we had today. So if you look, the theorem says is epsilon is greater or equal 0, xn is a typical sequences, and xn is emitted by the discrete memless source px. Then we have, again, we look at the probability of small xn, and see again that it's approximately 2 to the n minus h of x. And again, and the second case is also very similar. We look at the cardinality of Pn epsilon px, or the cardinality of the typical sequences. And again, this is approximately 2 to the n times the entropy of x. And then we look at the probability that a sequence is typical. And this is again really near to 1. And the proofs are again similar to the proof of the previous theorem. And therefore, I leave the proofs for the exercise on Thursday.